Euler's method. Becca's going to read the first paragraph.
For differential equations that cannot be solved, a slope field provides a graphical solution to the differential equation. The problem with this approach is that a slope field is only really good for getting general trends in solutions and for long-term behavior of solutions. There are times when we will need something more. For example, it is sometimes useful to know how a specific solution behaves, including some values that this solution will take.
All right, pick some by.
Danielle.
In these cases, we must report to numerical methods that will allow us to approximate the solutions to differential equations. There are many different methods that can be used to approximate solutions to a differential equation. We have already seen one example, linearization, otherwise known as tangent line approximations, which can give us a decent approximation of a solution near a point of tangency. Today, we are going to look at a method devised by 18th century mathematician Leonhard Euler that expands upon this idea.
All right, pick some by.
Bailey. Okay, I want to say Euler. Euler's method basically involves walking out along a tightrope from an initial point along its tangent line. Instead of walking along the same line the whole time, as in the tangent line approximation, we change tangent lines with each step of length dx. This involves recalculating the point and slope after each step. This will produce a much more accurate approximation than simply using the original tangent line. The process itself is pretty easy and repetitive, and it is easier demonstrated with an example rather than a complicated formula.
All right, perfect. All right, so if we have a curve, kind of like that, sounds great. If I have a point here, my tangent line goes like that, true? True. Okay, and the longer we go out, the greater my dx, the further away from my actual curve it's getting. Agreed? Yes. So what Euler's method does is it goes out a certain width, a certain dx, and then it recalculates with this slope, and then it kind of goes another tangent line with that slope. And then it goes out whatever dx that is, and then it goes out more. And so that's actually what Euler's method is doing. And the lower the dx, just like when we did secants to tangent lines and when we did our area under a curve, the lower we get our dx, the closer approximation we're going to get. Does that make sense? All right, so let's put it into practice. Here we go. So I have this differential, x minus 2, and I have this y of 0 equals 5. And that y of 0 equals 5 is our what? Initial condition. All right? And so what we're going to do is basically a repetitive tangent line. Okay? However, our tangent lines are going to change. And the way I do it is with an ordered pair method. That's kind of how I do it. So we're going to have 0, 5. That's our first ordered pair. That's what it gives us. That's our initial condition. And I need to get to approximate 0.8. All right? Using how many steps? 2 steps. So eventually I need to get to 0.8. Right? So what's my other one going to be if I need to do 2 steps? 0.4. So I'm going to say 0.4 comma blank, and that's what I need to solve for. And then I'm going to get to 0.8. Okay? All right? So what 2 things do I need in order to have a tangent line? A point and a slope. So I'm going to use my first point to make a tangent line. So what is that? My first point is 0, 5, right? And so what is my slope there? -2. So now I'm going to say 5, because that's where my point starts. And then I'm going to have a slope of -2. How do we get -2? We substitute in what? 0 in there. All right? And then I have like x minus 0, right? So my x is actually going to be 0.4, because that's my step. All right? And then it's technically -0, but we don't need that. So now I just have a step of 0.4. You see how that works? All right. So now, what do we get? We get 5 minus what? 0.8. Well, 5 minus 0.8 is, what is it? 4.2. So now I have my ordered pair as 0.4 comma 4.2. And I'm going to do it again. All right. So now, where do I start? I start at 4.2. Minus, now I need a new slope. So how do I substitute? What do I substitute in? 0.4. So now I'm substituting in 0.4. right there. So what is my slope now? Negative 1.6. So now I have a negative 1.6 slope. And what's my step? 0.4. Technically what's happening here is it's 0.8 minus 0.4. All right? But I don't really say that. It's just my step of 0.4. All right? So now we have to do a little bit of math. All right? So now we got 4.2 minus what? What is 1.6 times 0.4? 0.64. And so now we have 4.2 minus 0.64, which is 3.56. So now my ordered pair is 0.8, comma 3.56. So the way I want you to give the answer, though, is the approximation of that. I'm going to say of y of 0.8. What do I say? Squigglies is 3.56. All right. Pretty good? All right. Now, that's using Euler's method. On this one, though, can you actually solve for it? We can actually solve for 0.8. Yeah. And so I want to here. All right? So the first step is to do what? Separate. So let's separate this differential. So I'd have dy is equal to what? The quantity of x minus 2 dx. All right? And so now, what's my antiderivatives? Y is equal to x squared over 2 minus 2x plus c. Now what do we need to solve for? C. I need to solve for c by substituting in my initial condition. All right? So my x is 0. My c is actually what? 5. Now I'm going to take that and I'm going to substitute back in. All right? So now I have the equation y is equal to x squared over 2 minus 2x plus 5. Now, what am I trying to solve for? At what? 0.8. So now we have y of 0.8. 8 is 3.72. Now, is it kind of close? Kind of, sort of. All right? Would it be closer than just using a tangent line? Yes. How can we get closer? More steps. All right? However, are all differentials solvable? They're not. All right? So here we go. Let's look at this one. So I have dy dx is equal to 2x minus y. And then I have an initial condition, y equals 3 when x equals 2. I don't like it written like that. How am I going to write it? I think it's 2 comma 3. And then we're going to use Euler's method to approximate y when x equals 1.7. So I'm using 3 steps now. First of all, can I solve this differential? No. Can you separate this? Nope, on a rope. So guess what? We need more methods, and that's why Euler came up with this. All right? So I'm going to rate my ordered pairs. I start out at 2 comma 3. Then, what are my next ordered pairs going to be if I need 3 steps when I get to 1.7? 1.9, then 1.8, and then 1.7. Now, what is my step size? It's not 0.1. It's negative 0.1. Why is it negative? Because I'm going down. All right, good? All right, fantastic. So now let's do it. So, what do I start out with? 3, and then I need to find my slope. So I'm using 2, 3. So when I substitute in 2, 3, what's my slope? 1. All right. So now I have plus 1 times, what's my step? Negative 0.1. All right. Technically, it's like x minus 2, right? But what's my x going to be? 1.9. So it's 1.9 minus 2. You following me? All right, so now I do a little bit of math. 1 times negative 0.1 plus 3 is 2.9. So now I have my next ordered pair as 1.9 comma 2.9. You see how it's kind of like a repeated tangent line? All right, so now I have 2.9. Plus, now I need a new slope. So I'm going to substitute in 1.9 and 2.9 in there. So I end up with, what's 2 times 1.9? 3.8 minus 2.9 is 0.9 times negative 0.1. All right. So now what's 0.9 times negative 0.1? Negative 0.09. All right. So now I subtract that or add that, I guess, to 2.9, and I end up with 2.81. Love it. So now I have the ordered pair as
1.8, 2.81.
all right. It's getting better. All right. All right. So what's my next one? Where do I start out at? 2.81. And then I need a new slope. So 2 times 1.8 is 3.6 minus 2.81. So my new slope is 0.79 times my step of negative 0.1. All right. All right. So then I end up having 2.81 minus 0.079. And so I end up with 2.731. All right. And so this is where I can make my squigglies. So what do I say? Y of
1.7
is
equals approximation.
squiggly 2.731. Here we go. Example 3, assume that f and f prime have the given values. Use Euler's with 2 steps, 2 equal steps to approximate the value of f of 2.6. All right, here we go. So basically, I kind of want you to write ordered pairs again. That's the way I'd suggest you doing it. All right, so now my first ordered pair is 3, 2. My next ordered pair would be 2.8, something. And then my next word pair is 2.6, something. All right. So here we go. So now I'd have 2. We need a point and a slope, right? Yes. 2. And then what is my slope there? 0.4. Times, what is my step? No. Negative 0.2. Why is it negative, guys? Because it's going backwards. It's going down. All right. So here we go. 0.4 times negative 0.2 is 0.08. All right. So now I end up with 1.92. So now I have 2.8, 1.92. All right. So now, where do I start? 1.92 plus, what is my next slope I need? 0.7. And then times, what's my step? Negative 0.2. So 0.7 times negative 0.2 is negative 0.14. All right. So then 1.92 minus 0.14 is 1.78. So how do I notate it? F of 2.6 is about equal to, squigglies, 1.78. What part of this information is not needed? I want to go over this. The 0.9. When would that 0.9 be needed? If I needed to find f of what? 2.4. Does that make sense? All right, we're not actually getting to that step. Okay? All right, let's keep moving. Who read last? Bailey, pick somebody.
Example 4. Consider the differential equation dy dx equals that thing. Let y equal f of x be the particular solution to the differential equation with initial condition f of 0 equals -1. Part A. Find the limit as x approaches 0. Show the work that leads to your answer.
All right, what do we try to do first on a limit? Direct substitute. What happened? I get 0 over 0. So I need to say f of x, my limit, as x approaches 0 of f of x plus 1 is equal to 0. And I'm going to have a limit as x approaches 0 of sine x is equal to 0, then what? L'Hopital. We're L'Hopitaling. So the limit as x approaches 0 of f prime of x over cosine x. Now, what is f prime basically doing? Using that differential. All right. So what is my y? -1. So now I have -1 quantity squared, which is 1, and then times 2. So what do I get in my numerator? 2 over, what is the cosine of 0? 1, so 2 times 1, or 2 over 1 is 2. All right, pretty good? Awesome. All right, next part.
Part B, using Euler's method, starting at x equals 0 with two steps of equal size to approximate f of 1.
All right, fantastic. So this is where I definitely advise using fractions. It's going to make your life a little easier. So what's my first ordered pair? 0, -1. And then what's my next ordered pair? 1/4, comma, something. And then what's my next ordered pair? 1/2. All right, so what's my step here? Positive 1/4. All right, pretty good? All right, let's do it. So then, where do I start? -1. And then plus, what is my slope at -1, or 0, -1? We just found it. 2. So now I have 2. And then times my step of 1/4. Okay? So now 2 times 1/4 is 1/2. -1 plus 1/2 is cool.
I like this. Fractions are better.
Fractions are friends.
All right, fraction of friends. I agree. All right, so now let's start it out. So what is my y1? -1/2. And then now this is where we need our new slope. This is where fractions will be nice. Let's go off to the side a little bit. All right, so my y squared is going to be what? -1/2 quantity squared is 1/4. You guys see where we're substituting in right there? All right. And then times 2 times what?
No.
Just 1/4, right?
Yes.
And then plus 2. All right. So let's do some stuff here. 2 times 1/4 is 1/2 plus 2. How do I want you to think of that? 5 halves. Good. So 5 halves messes with 1/4 to be what? 5/8. Love it. Then what am I multiplying with? 1/4. All right. So 5/8 times 1/4 is
532.
5/32. 5/32s. All right. So we got 5/32s, and then -1/2. How do I want to think of -1/2? -16 32s. And so I end up with -11 32s. So how do I want you to write your answer?
Y, F.
No, f of 1/2 squiggly equals -11 half. Whatever. All right, perfect. So next part.
Oh, find y equals f of x, the particular solution to the differential equation with initial condition f of 0 equals negative.
All right, what do we have to do? First, separate. All right, so let's separate. So on my left side, what do I get? dy over y squared is equal to 2x plus 2 times dx. Then what?
Integrate.
We integrate. All right, so what's my antiderivative? -1 over y is equal to?
X squared plus 2x plus c.
All right, what do we solve for? Freaking c. So what does c equal? C equals 1. That was convenient. All right, so now I back substitute. So now I end up having -1 over y is equal to x squared plus 2x plus 1. Then what's y equal? -1 over x squared plus 2x plus 1. Now, what do we get to substitute? Oh, you know what? It doesn't ask for it, but we're doing it. So now, I want to see how close this is to our actual. just because I want to. All right, what would we do? We substitute in what? 1/2. So I want to find it. So we're going to find y of 1/2. So we get -4/9. All right.